us now take a look at the complete flow sheet for the solution of the Naviswix equations, so that we have a good idea of not only how we are solving together, but what is actually needed to get a solution. We are of course looking at first of all the steady case, and we can see how that is going to be changed when we look at an unsteady case, where we want to get a time accurate resolution of the velocity field and the pressure field for a general 3-dimensional flow. We are restricting ourselves as of now to a Cartesian flow geometry. In the next part of the course, we will look at the general case of a complicated geometry which does not necessarily fit in a Cartesian coordinate frame. So we will look at an outline of the calculation procedure using the simple algorithm. Let us recall what the simple algorithm is. We have the Navier-Stokes equations, for incompressible flow consisting of the continuity equation which we can write as dou uk by dou xk equal to 0, and we have the x momentum equation, y momentum equation and z momentum equation, and each of these will have terms representing the rate of accumulation of x momentum or y momentum, z momentum, and the net advection of the x momentum, and the contribution of the pressure gradient and the contribution of the viscous stresses. These are the terms that appear in this, and in the method, in the simple method, we have a discretized x momentum equation which can be written in this form. Discretized about point P for the velocity at that particular point, plus A and B, U and B, where NB represents the neighboring points, and what those neighboring points depends on the specific discretization scheme that we adopt for the advection term and for the diffusion term. If you take upwind scheme, you have one set. If you take a central scheme, you have another effect, and if you take a second order or third order upwind, you have a different set of neighboring points. So depending on what kind of discretization scheme we adopt, we will have different neighboring points. But the point that we are making is that the velocity at a particular node will have contribution coming from the neighboring points, the effect of which is linearized into these coefficients. So we are looking at a linearized x momentum equations, linearized discretized x momentum equation, in which the effect of the neighboring points coming from the advection and diffusion terms is incorporated already here, and this is written as you have the pressure gradient term. So we can write that as 1 by rho Pe minus Pp. So this is the discretized form of the x momentum equation for a particular point, and if we write it for all the points, then we can write a corresponding matrix equation A1 u equal to B1, where B1 contains all the terms coming from the pressure gradient terms here, and A1 has the component for this and then the coefficients for the neighboring terms also. And we notice that if you want to solve this equation, then we need to know the neighboring values, and not only that, for the general case these coefficients here, these linearized coefficients, also contain the velocity components and the y momentum and z momentum. So in that sense, this A1 here contains approximations from linearization and approximations from the current estimate of the values of the v and w components in the x momentum equation. Okay, so we have this, and we can solve this provided we know all the coefficients of a1 and all the coefficients of b1. So therefore, because we have linkage of the x momentum with the y momentum and z momentum through the velocity components which are entering in this linearized in these coefficients here, and also because of the pressure which is coming here, we start the solution with a guessed pressure field. When we say guessed pressure field, we are saying that pressure at every point wherever pressure is to be evaluated is specified. You may start with 0 0 or 1 1 or whatever it is, or you can take the inlet estimate and outlet estimate of the pressure and you can do a linear interpolation. So whatever it is, you start with a guessed pressure field here, and once you specify the guessed pressure field, then B1 is known, and A1 is already known from some sort of linearization with some assumed values of u and v. Okay, so now we are in a position to solve this, and when we solve this we get u at all the points at which we have applied this formula here, this template here. So we know u as a function of x, y and z, or xi, yj and zk at those discrete points at which u is going to be evaluated. Now but this u is evaluated based on a guessed pressure field, so we call this as u star. This is not a fully correct one because this has had some guess values of pressure and also guess values of v and w, and similarly we can discretize the y momentum equation to get a2v equal to b2. Even in the y momentum equation you have a corresponding contribution from pressure coming as p naught minus p like this, and the same pressure field that we have used in the y moment in the x momentum is also used here to get this, and this is based on a star thing. This is also based on a starred velocity field, especially for the unknown components. So we solve this to get v star again as a function of xi, yj and zk. We notice that if you are using a staggered grid, then the xi coming in the u momentum equation is different from the xi coming in the y momentum equation. Okay. And we can do the same thing for the z momentum, and we can come up with a3w equal to b3, which is the linearized form of the z momentum equation. With a guessed pressure field we evaluate the w to get w star at xi, yj and zk. Now we introduce a pressure correction, the p star of x, y, z again at discrete points xi, yj, zk is now being supplemented with a guessed with a correction which we call as p prime, and this again is to be specified at yi, xi, yj, zk. As of now this is not known. Okay, we want to introduce this pressure correction in such a way that this pressure correction introduces velocity correction in the three velocity components v prime, u prime, v prime, w prime, such that the new pressure field, the new velocity field, that is u prime plus u star, v prime plus v star plus w prime plus w star, this is the new velocity field, satisfies the continuity equation. So the condition for evaluating the pressure correction is that the induced velocity corrections in this will satisfy the continuity equation, the discretized form of the continuity equation, and we can write this as okay, let's just put it as A1 times UE minus UW plus A2 times V north minus V south plus A3 times W front minus W back equal to 0, where this UE, U, these U's are the new velocities, and this we know is at x, all xi, yj, zk, so you can put these things. So based on the substitution of these things, we can get a modified continuity equation in terms of the known velocities u star, v star, w star, and u prime, v prime, w prime. So that equation cannot be solved directly because we do not know what this u prime, v prime, w prime are. So what we do in the simple method is that based on this discretization, neglecting the contribution of the neighboring points, we say as a first approximation this u prime a prime ap u prime is roughly equal to minus 1 by rho p prime e minus p prime p, and similarly okay, we will call this as APU for the u equation, and APV for the v prime equation is roughly equal to minus 1 by rho p prime north minus p prime p, and APW is the component, is the coefficient of the W p is roughly prime is equal to minus 1 by rho p front minus pp. So we use these approximate relations to get u prime, v prime, w prime, and once these are substituted into this equation along with the u star, then we get an equation, a pressure correction equation, which can be written as A4 P prime equal to B4, with all the coefficients of B4 are known and all the coefficients A4 also can be derived. So this we can solve for P prime, and once we get P prime here, then from these relations we evaluate u prime, v prime, and w prime from these approximate relations. So once we have this, all these corrections to the pressure and velocity field, then from these things we derive P nu as P star plus alpha P times P prime, and similarly u nu is u star plus alpha u times u prime, and v nu is equal to v star plus alpha v times the estimated v prime, and w nu is w star plus alpha w times w prime, where alpha p, alpha u, alpha v, and alpha w are under relaxation factors. They are positive, greater than 0, and they lie between 1, between 0 and 1. If you make them 0, then that means that P nu is the same as the P old, P star. If you make them 1, we are doing the entire thing. Once we do this, then it is known that the resulting iterative scheme does not converge. So we typically have them as of the order of 0.5 to 0.8. like this. Okay, so what we have done is through this discretization here, making the approximations for this influence of the pressure correction on the respective velocity corrections on a simplified form of the momentum, discretized momentum equation. We are able to go from the old values to the new values. So these new values are not fully correct because these are based on a guessed velocity, guessed pressure field, and also the coefficients that are coming in the A1 in the discretized individual momentum equations have some estimated values of y and u, v and w. Okay. Similarly, this one will have estimated values of u and w and so on. So this is not necessarily fully correct. It won't satisfy the momentum equations and continuity equation, and it won't satisfy the continuity equation because these are less than 1, okay, and also because these are only estimated values. So we have to start this process of evaluating these with the new values. Okay, so we are starting with this, and then we go through this process of the pressure correction equation and then get the corrections for the 4 components here, and then we come to this, and then we go back to this with the new values of pressure and velocities. We reevaluate B1, we reevaluate the coefficients of A1 and of course B2 and A2 and B3 and A3. We again solve for new values here. We put these things into this and into this to get new A4 and B4. We again solve for P prime and get, we can do this iteration several times. Okay, so and this is how we solve the Naviswix equations using the method which is known as simple semi-implicit method for pressure linked equations. And the semi-implicitness idea is coming from the fact that the velocity corrections for a pressure correction are obtained by neglecting, not by completely solving this, okay, but only by neglecting the contribution of this. So it is only partly implicit. This part is not implicit, this is in a way explicit step, but the fact that we are solving this together several times through this makes it that we are looking at an overall implicit scheme, but part of which is explicit. Okay, so this method is what we want to suggest as the method for the simultaneous solution of the Naviswix equations for incompressible flows. There are methods whereby this assumption, that is neglecting this, is avoided. For example, you can say that the velocity correction in the neighboring points is roughly the same as the velocity correction at point at this. So instead of completely neglecting this, you can make a contribution of this term which is equal to this. So you can say that instead of u and b, you can say u and b prime here, so that u and b, you can say that u and b prime is equal to up prime, u prime p, so that this expression here will become this plus a and b. Okay, so that gives you a different estimate for this u prime. So we can do those kind of things, and you can also, having known this u prime, v prime, w prime here, you can now come back to these estimate here. You can substitute these values in this and get a different estimate of u prime from this equation, and then we can put it back again into the pressure correction equation, and you can do it. There are many variants that are possible in this process. and there are simple, simpler, simple C, piezo. These are all simplest, these are all variants of the same idea with modifications centered around the evaluation of the pressure velocity corrections coming from the pressure corrections, and how many times you do this before you do this entire over this outer iteration. So these are the kind of things, but essentially this is one good way of solving the Naviswix equations. So with this we can claim that we know how to solve the Naviswix equations. Now what we have looked at is for a case of steady flow. If you have unsteady flow, then you may have an equation like dou ui by dou t plus dou by dou xj of ui uj equal to minus 1 by rho dou p by dou xi plus nu ui by dou xj. So far we have looked at this part. For this part alone we have gone through this, and we can write this whole thing as ui n plus 1 minus ui n by delta t, depending on what kind of discretization scheme, plus the discretized form of this whole thing, okay, is equal to minus of the discretized form of this thing like this. So now this becomes also part of this up, okay, and this becomes part of the unknown coefficient on this side. So in an unsteady flow, the discretized momentum equation will change slightly. The AP term will not only have contribution from the advection term and the diffusion term, it will also have a contribution from the unsteady term, okay, and the right hand side will have contribution from the previous time step value at that particular point. So that is the only modification to the discretized form of the momentum equations. With the continuity equation is exactly of the same form for steady and unsteady flows. Okay, so when we are doing an unsteady calculation using the simple method, then the momentum equations will be modified slightly, but they still are of the same form. That is, we have a1 u equal to b1, where a1 has contribution from the main point plus these things, and the contribution here is now the same contribution that we have from the advection diffusion term, plus, for example, this will give us 1 by delta t. So you will have AP plus 1 by delta t will be coming here, and here we will have plus 1 by delta t times uin will be coming in this. So in this way we have a modification to the coefficients here, but otherwise the solution method will be the same, and if we follow the solution method, then ultimately the velocities that we get will be the velocities at the new time step. Then with those time steps we have to come back to the discretized form and go from n plus 1 to n plus 2 and n plus 2 to n plus 3 and so on until we stop the calculation. So in an unsteady calculation we have to go through the solution of this iterative solution of guessed pressure field, estimated velocity field, estimated pressure and velocity corrections to the new values, and this kind of looping we have to do several times at each time step, at the end of which we get the new values of the flow variables at that time step, and then we have to go to the next time step. So the solution method is not very different, and so the extension of the simple method that we have looked at for steady flows to unsteady flows is relatively straightforward. So with this we can claim now that we know how to solve, not only we know what equations to solve, but we also know how to discretize them appropriately so that we get a satisfactory solution, and not only that, we know how to club them together, especially for incompressible flows, in such a way that we can through a lot of effort we can get the velocity field and pressure field for a given transient 3-dimensional case. But all that is not finished yet unless we have an efficient way of solving a matrix equation of this type of form. We need to have an efficient scheme, because in each step from going from star quantities to the new quantities, we have to solve 4 matrix equations, and we have to solve them many times, and each time with an updated A1, A2, A3. So we are not solving the same matrices all the time. So that puts some extra care that we have to do to make sure that we have an efficient method, and in a time dependent case we have to solve them many times at each time step to make forward. So the computational effort for a general transient 3-dimensional case is not trivial, and it will be extremely prohibitive unless we have an efficient way of solving this. Okay, so that is why it is important. The second reason why this is why an efficient way of solving these things is important is that the accuracy of the discretization, given that we are not solving the exact equations in CFD, we are solving only the discretized form of the equations. So the accuracy of the discretization depends on the truncation term, and we know that the truncation terms depend on delta x, delta y, delta z, delta t. So the smaller the delta x is, the smaller the delta t is, the more accurate will be the approximation of the governing equation, and therefore the more accurate will be the computed solution. So we need to make sure that we have sufficiently fine grid, fine discretization in order to get an accurate estimation of the flow variables. But for the same domain, if we want to have finer grid, then we have to put more number of points, so that will reduce the delta x, and when delta x is reduced we have more number of points, the size of this matrix becomes large, and once this becomes large, then the computational time required for the solution will also become large. Just to give an example, if we use the Kramers rule for the solution of Ax equal to b with n as the number of variables, then the number of mathematical operations is n plus 1, I think n minus 1 factorial, and so when n is 3, 4 like that, then it becomes a good method, but when n is of the order of 100, 1000, 10,000, 1 million, these are not unheard of numbers in terms of the number of grid points, and that is the kind of number of grid points that we need to have for a large domain where we want to get an accurate solution. So from that point of view, CFD is a brute method of getting a solution to the Naviswix equations, and it thrives only when you have raw computing power. Okay, so that is why as the computing power becomes more and more, we can go for more and more accurate solutions. So if you want to have an accurate solution, then we need to have a computer which can do lot of mathematical operations. When n is large, this becomes humongous. There are other methods like Gaussian elimination method, we will look at them, then where the number of mathematical operations varies as n cubed. Okay, so n cubed is not as prohibitive as this, as the factorial n factorial, and but even this can be very large. For example, if you take n to be million, so the number of grid points is million, then the number of mathematical operations that you have will be, let us call this as capital N. So the capital N will be of the order of 10 to the power 6 cubed, so that is 10 to the power 18 mathematical operations are needed. So when you say mathematical operations, it's multiplication, division type of thing. And a good computer, maybe until a few years ago, a teraflop machine is considered to be a good fast number crunching machine. A teraflop machine can do 10 to the power operations per second. So 10 to the power 12 mathematical operations per second. So if you were to use a teraflop machine to solve a million grid points, then the time required will be 10 to the power 18 divided by 10 to the power 12, so that is 10 to the power 6 seconds. And how much is 10 to the power 6 seconds? It is about 10 days. So if you have a grid of 1 million, and if you are using that a teraflop machine to solve just A1U equal to B1, this computation alone would take 10 days. And then we have to do this, and then we have to do this another day, another 10 days, 10 days. So that's about 1 month for getting this, and then we have this one, that's another 10 days, and after 40 days we get a new velocity field, and then we have to come back and then do this. It will easily take a lifetime of one particular person to get a solution for a decent thing. Okay, so when you have the number of operations varying as n cubed, then as n becomes larger and larger, the number of mathematical operations becomes even more larger at a much faster rate. Okay, so that's why we need to be very wary of making the problem size large. Okay, but it is necessary to have large number of grid points in a CFD computation, and these should be distributed all over the control volume so as to get a proper solution in a general 3-dimensional case. So in such a case, we have to have a method which is much faster than, much more efficient than n cubed in order to get a decent computational time. So if you had a method in which the number of mathematical operations varies as n square, okay, so if it is n square, then the number of mathematical operations required for the same million things will be about 10 to the power 12, and the time required for one computation will be 10 to the power 12 divided by 10 to the power 12, so that is 1 second, which is much more affordable. So in 1 second we can solve million equations, another second, 4 seconds for the 4 values, and we can do 1000 of those things, then we can get a solution in 4000 seconds, so it is about an hour. So how efficient the computation is, how efficient the computation of the solution of this matrix equation is very important. If it varies as, if the number of operations varies as n cubed, which is considered as an efficient method, which is characteristic of, for example, the Gaussian elimination method, that is not good enough for us, because that would take very large number of large amount of time even for a single equation. So if you have n square, then we can do easily 1 million operations, 1 million grid points, but even 1 million is probably not too high. These days people are running even with 10 million, or even with in some cases Naviswix equations are done even with much more larger number of grid points, because the more the computing power you have, the more realistic your representation of complicated geometries, the more the number of components, physical components that are affecting the flow domain that can be considered. Okay. So the search for efficient and more efficient algorithms is continuing, and these days we have methods in which the mathematical operations varies almost linearly with the number of nodes that are to be resolved. Okay. So it is important to have a good grasp of, good command of how to solve these equations together. Okay. And the conventional method for the solution of simultaneous equations, Ax equal to b, which is the Gaussian elimination kind of thing with n cube number of operations, is not good enough. So we have to have better methods, and that is what we are going to do. So we would like to now identify a method of solution of Ax equal to b in a reasonably efficient way, so that once we club it with the overall computational scheme that is described here, then we will have prescribed the complete method for the numerical solution of the Navier-Stokes equation. So without that, without an efficient method for the solution of Ax equal to b type of equations, the method is not useful. Okay, the method is not complete. So we look at solution of linear algebraic equations. What we mean by linear is the type of equation like a1u equal to b1, in which all the elements of b1 and a1 are known coefficients. Okay, they are numerical values. We see the origin of these things. They are coming from the pressure gradient. In the simple case, they are coming from the pressure gradient and maybe from the previous time step value here, and a1 comes from the diffusion equation and also from the advection term. In the simple laminar flow case, this constitutes a linear, this constitutes a nonlinear term, whereas this constitutes a linear coefficient. So in a simple laminar flow case with constant property, then this will only give us linear values, okay, constant coefficients, whereas this can give rise to first of all nonlinear coefficients. For example, we will have dou by dou x of u square, and it will also give rise to undetermined variable coefficients from times from iteration to iteration, because when you have dou by dou y of uv, then which appears in the x momentum equation, the discretization for u here will have an assumed value of v. Okay, so that assumed value of v will come in as part of the coefficient here. So the next time round when you come here, that assumed value will change because you have got a new value of v, and therefore from one iteration to another iteration the coefficient here changes. But we are looking at, when we come to the solution of this, we are looking at a linearized momentum equation. Therefore the value, all the elements of a1 and b1 are known, and we have a linear equation. So we can write it in the general term as a phi equal to b, where phi is a set of unknowns, and a can be, for example, a11 phi 1 plus a12 phi 2 plus a13 phi 3 equal to b1. We will put one more, a14 phi 4 equal to b1. So we are looking at a system of 4 equations and 4 unknowns, a21 phi 1 plus a22 phi 2 plus a23 phi 3 plus a24 phi 4 equal to b2, and a31 phi 1 plus A3252 plus A3353 plus A3454 is equal to B3, and A4151 plus A4252 plus A4353 plus A4454 equal to B4. If you have a million equations, you will have million of these equations like this with million coefficients coming here. So that is as big a set of equations that we are trying to solve. Okay. We are looking at a set of equations like this in which all the b's and all the aij's are known, and what are unknown are all the phi's. Okay. So this is the unknown, this is the variable, this contains the elements, the variable elements which we want to solve for known values of aij and bk. The solution of this type of thing can be done in many ways. Okay, so there are, one can say that there are three broad classifications. One is that we can solve this using direct method, and we can solve this using iterative method, and as usual when you have two classifications, there is one more classification which is a combination of direct and iterative. Methods. Okay, so we can have a large family of these methods, and among the direct methods, so when we say what we mean by direct method is a method is an algorithm whereby we do manipulation of these equations as per a given algorithm, and after a finite sequence of those finite number of and a sequence of this manipulations, we finally get the values of phi I. Okay, so that means that a direct method has a sequence of operations, mathematical operations that are needed to be carried out in this on these equations, at the end of which we get a solution. So the number of mathematical operations, by which we mean addition, subtraction, multiplication and division, and when we look at the computational time, typically we take only the multiplication and division because these are more time consuming than addition and subtraction. So the number of mathematical operations that are to be done on this system of equations in order to get the solution is fixed in a direct method. Okay, so this means that this has a fixed number of mathematical operations, and at the end, typically at the end of those fixed number of operations we get the solution. So if you have a million number of operations to be done, typically towards the end or at the end we get all the values, but and towards the end we typically get most of the values. Iterative methods are, they have a totally different principle. You start with a guess value and you try to improve upon it in such a way that these equations are somehow solved, okay, in their approximate formation. So you go from a guess value to an improved value, and then you put back the improved value in your algorithm to find an approximate value, okay, and then you put that improved value back into that black box which describes which comprises those kind of operations that are needed to get the improved value. So you put back the improved value into the black box, and then you get a further improved value, and then you put it back like this. You do it many times until you get a more and more improved value. So these are characterized typically by an ever improving value. Okay, when we say ever improving value, you need to say what is the most correct value, what is the correct value, will it ever reach the correct value. typically these iterative methods asymptotically reach the correct value, and any asymptotic thing is infinite number of steps. Okay, we do have a limitation in terms of the machine accuracy of computation when we do it numerically using a computer, but typically we have a very large number of calculations that are required to get to that asymptotically exact values. Okay, by definition you don't reach the exact value when we are looking at infinite accuracy of computation. So we have to stop at a particular point. We say that a 4th decimal accuracy is good enough, or a 10th decimal accuracy is good enough. So we use that kind of judgment, or another objective way of judgment expressed typically in terms of norms of the residual. Okay, so we make use of some criterion like that to say that this is where we have got an accuracy which is good enough for us. So the end is specified in terms of some estimate of the goodness of the accuracy that is required, otherwise there is no end. So we have an infinite, theoretically infinite number of math operations, theoretically, but practically we put a stop to the iteration. After some number, and where we put a stop is not necessarily easy to estimate. Okay, so sometimes you may have to go through that is, by the time you start the computation, so at a priori you don't know how long it will take to get to that satisfactory solution. So that is a typical characteristic of iterative methods, although one can do some estimates of that. So in theory they have infinite number of mathematical operations, but practically we can, if you put an accuracy on the level of solution, then we can get some estimate of the number of mathematical operations required for this. So there is in a way no end to this, but will end at some point. So these are two very contrasting approaches to the solution of a phi equal to b. Let's put some names to this so that we can recognize these things. The Kramers rule is one method, or one direct method, which we straightaway discard in any CFD computation because of the number of mathematical operations that are required for this. Gaussian elimination is one very good way of solving a system of equations, and this is a direct method. You have a finite number of operations at which you get a solution. And we have another method, again LU decomposition. Okay, so this is another useful method, and we have also the Gauss-Jordan method, and there are some more methods which are more specific, like the tridiagonal method for a specific type of form of the coefficient matrix, and then you have the cyclic method, which is again for a specific type of specific structure of the coefficient matrix, and so on. So, and we can say that these, and there are also other methods which can be called as direct methods in theory, but because of finite accuracy of computation numerically they become some way iterative methods. We will look at we'll mention those things later on, but we can identify these, and also in the context of CFD we can call this as tri-diagonal matrix algorithm and pentadiagonal matrix algorithms. Okay, so these are something in a way these are variants of the Gaussian elimination for special structure, and even LU decomposition can be considered as a variant of the Gaussian elimination method. And so these are some of the things that we may be using, and among the iterative methods we have the Jacobi method, we have already seen the Gauss-Seidel method, and we have the successive over relaxation method, and we also have methods like ADI method, alternating direction implicit type of methods, and we also have other methods which we can leave at this stage. For example, the conjugate gradient method, it is a fairly complicated method which is in principle a direct method if you have infinite accuracy, but which is usually put as a used in the context of an iterative method when we have finite calculation, finite accuracy of calculation, and so this may come as iterative method, and typically this comes as part of the combination of direct and iterative methods. So we have identified already the conjugate gradient method, and of course we can say that even ADI method is a conjugate gradient. We can say that there are variants of successive over relaxation which will come in this. So conjugate gradient method, and then we have some combination methods like strongly implicit procedure and its variants, where we try to take in the combination methods, we try to take the advantage of specific features of the direct methods and specific features of the iterative methods to come up with a combination algorithm which is better than both of this. And then we can even say that we have already mentioned conjugate gradient here. A multigrid method, although it is it has a different philosophy to the overall solution, is a method which is worth mentioning, and it may be called as an iterative method, but it's very difficult to put this into any of these classifications. Okay, it's a method, definitely it involves some element of iteration, and its extreme end it may use some direct method also. So we will just mention these things here, and at this point we will not go too much into the details, that we will postpone for the next lecture, but we would like to identify these methods in terms of the number of mathematical operations that are required. Okay, and especially what we are looking at is the exponent value. We have seen from this example a method which goes as n cubed may take something like 10 days for the solution of a million unknowns, and the same thing which takes as n square, where the exponent goes from 3 to 2, will take only about a second. So you have that much of variation just depending on what the exponent values for large matrices, for large number of grid points, and we want to have a method which is good for which is good also for large number of grid points. So the exponent here becomes very crucial. So how do these exponents vary? We cannot fix a value of exponent for an iterative method because in theory they go up to infinity, but when we put a practical stop, say at a 5-digit accuracy or 10-digit accuracy like that, then we can put a stop, and based on that we have some estimates for the exponent for this. Gaussian elimination, it varies as n cube by 3 number of operations. So this is a method which will take a large amount of time, maybe 3 days for a million grid points in its most straightforward form. And although it takes such a long time for a large number of grid points, it is considered as the best direct method for a solution of a general a phi equal to b type of equation. So that is when the matrix here A here is mostly filled, that is it has very few zeros, and if when it has no specific structure, then this is considered as the best method in the general case, best direct method in the general case. LE decomposition is in a way it is very similar to the Gaussian elimination method, and it also takes n cubed by 3 plus a small bit plus some n square number of terms. Okay, so for large values of n, this requires slightly more number of mathematical operations than this, and the two are very closely related. And both these methods, Gaussian elimination method and LE decomposition method, have the merit that they can be used under the most general conditions. There are no conditions on what this A should be except that they must be, the determinant is not 0. Okay, so in that sense these two methods can be applied for any matrix A. The TDMA and PDMA are methods that can be used only when there is a diagonal structure. The tridiagonal matrix algorithm is applicable only when you have 3 adjacent diagonals. Okay, so this one and then this one and this one are non-zero. Okay, so that is typically the kind of matrix structure that we have for one dimensional diffusion equation. And PDMA is something that can be used when you have 5 adjacent diagonals which are non-zero. Okay, so this kind of thing will be obtained for a one dimensional diffusion equation with 4th order accuracy. With the 2nd order accuracy you have 3 adjacent diagonals, with 4th order accuracy you have 5 adjacent diagonals. When you go to 2 dimensions, then you do not have either tridiagonal matrix algorithm or a pentadiagonal matrix algorithm. So only for a restricted number of restricted case you have this TDMA and PDMA thing, and TDMA varies as n to the power 1, okay, with a constant, with the coefficient here which is there. Okay, but still compared to the n cubed, a varying linearly is a great advantage. Okay, it is a humongous advantage. We can see that when you go from n cubed to n square for a large matrix, we have gone from days to seconds. Okay, and if it is 1, then it is a second to microsecond type of thing. But one would be foolish to try to do a one dimensional equation with such large number of grid points. It usually does not arise. Okay, so the applicability of this as a direct method for an overall solution is in a way questionable. Okay, but if you are solving for a one dimensional flow case with a diffusion term which gives you this type of matrix structure, then probably that is the best method to do. And PDMA will also be something similar, and this is even more rare because you are looking at a 4th order accuracy for a for a one dimensional equation. So that is even more rare, one dimensional diffusion equation. Typically we look for a 2nd order accuracy. Okay, so this is for direct methods. So the best general purpose direct method has an n cubed number of mathematical operations. Iterative methods, Jacobi method and Gauss-Seidel method typically have n square number of mathematical operations for reasonable accuracy of the solution. So they constitute a great improvement from days to seconds for the solution of the same equation, but there is a severe restriction on what kind of equation, what kind of matrix we can for this we can apply. These methods can be, the direct methods can be applied for all matrices where there is a unique solution, whereas the iterative methods here can be used only when you have for example the Scarborough criterion which I have mentioned here, the diagonal dominance condition is satisfied, only then we can say that we can say with confidence that this is these methods will converge. So these methods will work in the context of CFD for a convection diffusion equation of the generic scalar transport type of equation on orthogonal coordinate system. On a non-orthogonal coordinate system, then you have the resulting discretized equations will not be satisfying the diagonal dominance conditions, and in such a case these methods cannot be applied. Okay, so SOR, successive over relaxation, is an improvement on this, and an optimal value in a successive over relaxation. There are over relaxation parameters, just as we have under relaxation factors, we make use of over relaxation factors, and this will vary under optimal conditions as n 1.5. Okay, so we are going down from 2 to 1.5. So that again constitutes a big improvement. From second we can probably go down to millisecond or hundredth of a second for large kind of matrices, but it is not easy to find the optimal set of parameters, optimal set of over relaxation factors. We have to do more work, and there is something like that. And you can also have other methods which fall in between this, where you, since we cannot get optimal over relaxation parameters, there are methods by which we can find approximate values for them, and then get a mathematical convergence which probably falls somewhere between n square and n 1.5. These methods have restricted applicability. Conjugate gradient method is much more general. It can be one would say that it has been developed for symmetric matrices, but there are variants of that method which can be used even for asymmetric matrices. It is not necessary to have a diagonal dominance condition here. ADI is a combination of these two. It gives faster rate of convergence than say a simple Gauss-Seidel kind of thing, but probably not as fast as the SOR method. Conjugate gradient would be very good, and in its simplest form I think it can go up to 1.25. So we are getting down closer to this, but okay, that's very good, especially the rate of convergence is very good under optimal conditions. SIP is probably more like ADI. This will be somewhere between n square and n 1.5, although it is very difficult to pinpoint what exactly it is, but it is better than the Gauss-Seidel method kind of thing. Multigrade is a new philosophy. It can almost linear kind of computational efficiency is obtained with the multigrid method. Okay, so this is a range, a family of methods in which we can go from a general purpose method with n cube number, which takes 10 days, to n square, which is a general purpose iterative method with restrictions on what kind of A that we can use for, okay, to go to seconds, and then we can go to even milliseconds using conjugate gated method, which are again with some restrictions and so on, and with multi-grid method where we have to do much more work, and it may be, because for all the work it may be 1.1 or something like this. Okay, so we have a family of methods which can be used, and wherever it is possible we have to take advantage of the problem that we have and then come up with the most optimal way of solving this a phi equal to b, because we have to solve them so many times. We have to solve them here, 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 and then here, and then back here, and so many times we have to solve. So we will look at some of the methods, how these methods work in the next couple of lectures.